Okay, so a couple of sessions on discrete optimization. We look at submodular functions. We already got a flavor of how there is diminishing returns with the last example that you showed, right? The the cost of improving alignment with model size. There's certainly a diminishing return with respect to the parameter, right? Now, number of parameters. Um, so the big picture is, while we have dealt a lot with continuous optimization, discrete optimization problems surface in two ways. One is you can view them as the original problem to which continuous optimizations have been manifest as relaxations, right? That's one view. The other view is, well, there are certain problems which you can't relax. You would like to solve them as discrete optimization problems. And a third view is, well, a discrete optimization problem itself can help either hyperparameter tuning or network architecture search, help the continuous optimization problem. So facility location, set cover, graph cut, entropy, and so on. We'll hopefully at least run through one or two. So obviously we look at the discrete optimization only from a machine learning perspective. And one of the canonical problems here is, given a ground set, we want a subset of the ground set such that it maximizes a scoring function F. Okay, scoring function basically goes from the power set of the ground set to positive reals. We look at positive reals. Again, restrict our scope there. And summarization is one strong use case. Well, while large language models are capable of doing very good summarization, often if you want extractive summarization, um, you may want to look at the problem of maximizing a function such as f, such that f represents or f is um, synonymous with representation. You want a subset that represents the entire set. That's what you would typically like in a summarization. Like the generated sentences should summarize or represent the original set. So think of this S as a summary and think of this V as the original document. Yeah, so the V is the ground set and S is the summary for the ground set. Okay, so there are very nice books. Fiji Shige has a book on submodel functions optimization. I think many of these still remain very interesting in areas where data is not going to be plenty, or if data is plenty, you have resource constraints in which you want to learn with less GPU, or you want to annotate very frugally. So I firmly believe this is a very important area going forward. There are also a whole bunch of slides and tutorials I've presented. We have had tutorials at Ichikai. There was a tutorial at AAA also um, a year and a half back. A couple of other tutorials by others, not me or my group, but others. So if you recall, we had talked about some of these discrete optimization problems in computer vision, for example, image segmentation and image correspondence, right? These are from our earlier lecture. We talked about these, but we look at some more now. um, so we look at these examples from the point of view of submodular functions. So we'll first present the definition for submodular function, the intuition for submodularity, how powerful these functions can be. Okay, so these functions help solve combinatorial subset selection. So I have to explore this large power set, right, of the ground set. So in general, set function optimization is very hard, right? If I want a function maximization of the function with respect to a subset of V. But if there's some special structure, is it possible to choose a subset more effectively, right? And it turns out that yes, in practice, there are many functions which exhibit this property. Okay, and the simplest example here is presented in the form of an urn and balls in the urn. Each ball has a different color. So there are green and blue and red balls. Now, if F is the number of distinct colors of ball in each urn, in the first urn, let's say my earn on the left hand side is A. Okay, it's called the subset of balls here as A, and the subset of balls, and the ball that I'm adding, the blue ball that I'm adding is V, the element V. Okay, so if I look at the value of function f after I add V to the set A, it is basically 3: blue, green, and red. But if I look at the function value on A itself, it has 2 brown and 3 green. The number of distinct colored balls is just 2, or number of distinct colors of balls is just 2, right? So this is 2, though A itself has 5 balls, right? So the difference of F A union V and F of A is exactly 1. That's the left hand side. If you look at the right hand side, what I've done is I've added a few more balls to A, okay, and called it B. So this is B. What is B? B has 2 brown, 3 green, and 2 blue balls. Now the same ball V I'm going to add to B. But unfortunately, blue is already covered. So there's nothing more to cover. Right? 3 minus 3 is 0. Okay. So the left hand side, the marginal gain of adding the blue ball to a subset of balls is more than the marginal gain of adding the same ball to a superset of the same set of balls. Okay, so this is a notion of diminishing returns, and therefore it's very reminiscent of concave functions, right? You might say, oh, submodular functions are concave functions for discrete sets. How many of you think like that after seeing this example? They just appear like concave functions, right? You're shaking your head. Why? You can't just generalize. Any reason? Okay, so there's a lot of interesting work on submodular functions. In fact, a lot of work that has studied the convexity like properties of submodular functions. Okay, so I'm just going to draw a sketch. It's going to be mostly pens, text. So submodularity, is it convexity like or concavity like is the question. Okay. So concavity we have already seen. There's this diminishing returns. Is there anything that they would have like convex functions? Okay, it turns out that minimizing submodular functions is actually possible in polynomial time. Okay. Whereas if you had to maximize the submodular function, do they display concavity like properties? It's an NP-hard problem. Maximization is hard, right? So there are good polynomial time algorithms and greedy algorithms, right? So that's a positive, though very efficient greedy. Actually, it's not just efficient and effective. Greedy algos. Okay, so that's a saving grace. Therefore, they're still interesting, and therefore the entire submod lib library that put out by my former student. I mean, it's attractive because it brings in lots, not just algorithmic, but also engineering tricks into how you can maximize submodular functions well. The memoization tricks, right? There's lazy, greedy versions. In practice, they are pretty good, and they give actually from a machine learning perspective, there's been more interest in the concavity aspect. Okay, so that's the other difference. Uh, convexity aspects are more interesting from inference perspective, from say inference such as graphical model. For graphical model inference perspectives, convexity is generally more interesting, whereas concavity from ML, from learning perspective, it is a generic statement. Okay. Professor H. Narayanan, who was a star professor at our Department of Electrical Engineering, he has written books on the convex aspects of submodularity. But the applications in the concavity side have actually seen a lot of you know interest in the last few years. So, I mean, all of us. I mean, I hate to give this example. This is fast food example, but that's typically what people succumb to, right? Well, what happens is, if you go for a small set, right? So if you have this, some finger chips and something to drink with that, so you see the difference, right? The difference, um, more items you buy, the more the discount, right? So in terms of cost, yes, the difference between, and that's what is exploited, right? And you say buy more, then there's less value in adding, the incremental cost is less in adding a new element to your set. Yeah. Unfortunately, this is exploited by the consumerism industry. But in machine learning, if I have to do discrete labeling, okay, so I can certainly exploit some modularity. For example, I may look at coherence. So if I'm doing image segmentation, I might look at even the minimization aspect and find coherent sections of the image and say, well, please label these for me. So if you remember the image segmentation problem, it's kind of a on some modular minimization problem. Right? But you can also look at so likelihood. You see this graphical model. The moment I show graphical model, you think the segmentation is like a some modular minimization problem. So it's interesting from labeling perspective. But often you're also interested in diversity. Like the set of examples I want to show should be diverse enough, where some modular maximization becomes interesting. Okay. A second place is summarization. I already gave the example, right? So summarization is diminishing returns very obviously, relevance and diversity of coverage. The three broad function classes: representation, diversity, and set cover or coverage. Okay. So you see all these coming up here. So here you have relevance, which is representation, diversity, which is submodular. Okay. Or if I'm trying to set up place a bunch of sensors in this room, again, I give this example of data sets, selecting subsets of data points on which the stochastic batch gradients, how you compose the batches, right? I brought up this analogy of sensor placements in that context. So you would like to place these sensors in a way that it covers the classroom well. Now you can talk about two kinds of coverage. One is coverage of the actual instances or coverage in a feature space. So I may say, well, I want to cover individuals, people sitting in this room, or I might want to say, well, I want to cover features of individuals. Right. So when I talk about covering individuals, it's called representation. When I talk about covering features of individuals, it's called coverage. Okay, but they are different functions. But sensor placement is another example. Where to put sensors, which experiment to perform next, and so on. Okay, and modular functions are another function, functions which are both submodular, and their negative is also submodular. They're basically linear functions. F of S is summation over all elements in S of the weight of each element in S. So it's like a weight function. Okay. So now there are also monotone submodular functions. A lot of efficient greedy algorithms work out when there is monotonicity. Monotonicity basically means that as you increase the size of the set, as you keep adding elements to the set, then the function cannot decrease. So influence in social networks, right? Keep adding nodes, your influence cannot decrease. Even the coverage example I took in the previous slide, the coverage cannot decrease. And the most classic example is of entropy. Okay, entropy turns out to be a submodular function, and it's monotone as well. Right? As you keep adding elements, the entropy for a set of random variables cannot decrease. Uh, Another very interesting function is information gain function. The entropy of H minus entropy of entropy of Y minus entropy of Y given some condition, right? Now it turns out that it is submodular if uh, there is some kind of conditional independence. The Y's are conditionally independent of the X, conditionally independent of each other, conditioned on X is the naive Bayes assumption, right? Under naive Bayes assumption, this turns out to be monotone submodel. Okay, so in fact, information gain is always monotone, but only under certain conditions. Like I said, naive Bayes, it is submodular. So information gain is always monotone, but under naive Bayes, it's also submodular. Okay. And some other interesting points in the same slide is that, suppose entropy were both monotone and submodular, it would still not mean that there is no function that is submodular but not monotone. So point I'm trying to make is entropy is a very interesting subclass. In fact, Shannon's conditions on entropy very much coincide with another definition of submodularity, which I won't talk about, based on intersection and union. But this class of submodular functions is larger than that of entropy, right? Though the conditions were stated for entropy functions by Shannon. Okay, so yeah. So it's not necessary, by the way, that if the function is submodular, it must be monotone. It's not necessary at all. And a classic example of that is something called the determinantal point process, DPP. Now, DPP captures kind of volume, right? So if it's a little tricky to understand, but it may not be monotone. So as I keep, let's say I define a bunch of points, I give a bunch of points and ask you to find the volume of the polyhedron of which those points are the vertices. And if I add a new point, it's possible that the new point is inside the set and the volume doesn't increase actually, right? So it's non-monotone, but it turns out to be submodular. Okay, so not every monotone function is submodular. That's very obvious. Look at this example, 0, 1, 1, 3, right? It's monotone. But is it submodular? Can you check? In fact, it's strictly supermodular. Its negative is strictly submodular. We can check that, right? If you add V is ground set A comma B, and if you look at 3 minus B, right? 3, oh, sorry, so just remove B from here, right? F of A minus F of, you can verify that. It's easy to verify, right? F of A union B minus, or V, in this case B minus F of A should be greater than or equal to F of B union B minus F of B in the, F of B, which in this case can be again B. So, as I said, there's another diversity-based function such as log determinant and disparity mean sum, which are not submodular though they are monotone, which are not monotone though they are submodular. The other way. Okay. Not every monotone function is submodular and not every submodular function is monotone. Okay, so summarily, what are we saying? Well, we have monotone submodular functions, we have non-monotone submodular functions under this class of submodular functions, but there are also modular functions, and then there are functions which are monotone but not necessarily submodular. And the supermodular functions are basically complements of submodular. Negative of a supermodular function is a submodular function, and their intersection is exactly the space of modular functions. Okay, this is like a bird's eye view. Let's take few interesting properties. So convex combinations of submodular functions are submodular. Calculus is what we come to every time, right? Okay. For convexity, we talked about calculus. Subgradients, we talked about calculus. So intersections with fixed sets is submodular. If I have a fixed set, I like that set is like my projection. Think of this as projection, or it's called restriction. That's submodular. Okay. Union with fixed sets is submodular. It's called conditioning. Complements are submodular, right? So you can think of how these relate to the calculus with convex functions and so on. And there are actually two equivalent definitions of submodular functions. One we already gave, diminishing returns. The other is in terms of intersection union. I don't know if we'll have time to do that. And then I gave a hint, minimum and maximum submodular functions. For maximum, you can have greedy algorithms which are efficient, and minimum, there are polynomial time algorithms. Then you can derive information functions out of these. So if you look at the lectures from the last year where we didn't have course projects presentation, so I spent a lot of time on information functions and so on. So convex combinations, very obviously you can think of them as submodular, right? It's a no-brainer here, and you can prove that by first principles. Very simple. So in general, if f theta is submodular, if theta is just an index from a parameter index, then random variable, then summation over theta of p theta f theta is submodular. So if you take an expectation of multiple submodular functions, right, with respect to some distribution, then expectation is also submodular. So it's going to be useful for multi-criterion optimization. Right? So restriction, I give you just as an explanation of what was said earlier. If fs is submodular on V and W is subset of V, right? So this restriction, you're restricting S on W, right, this part. Then f dash defined on this restriction is a submodular. If originally f is submodular. Conditioning is like, okay, I have S, I have W. By default, I keep adding W to S. So that maintains submodularity. And reflection is if I take S, I'm going to take the reflection, which means I'll take the F on the complement of S. That's also submodular. Okay. So in these cases, W is fixed. That's something to note. Can't she keep changing W? So now the last point, the two equivalent definitions of submodularity. One is diminishing gains, which we saw earlier, right? But there's another one, which is union intersection. So f of A plus f of B is greater than or equal to f of A union B plus f of A intersection B. So what is this? Like if I look at set cardinality, I know that cardinality of A plus cardinality of B is the same as cardinality of A union B plus cardinality of A intersection B. So because you're doubly counting the intersection. So here it turns out that no, doubly counting the intersection doesn't happen. Slightly, this is more than doubly counting the intersection. F of A plus f of B is more than doubly counting the intersection. Right? I mean, you can view this from this perspective that, if I add the intersection to f of A union B, I'm not going to get as much as if I were to keep A and B separate. So think this is, I just want to leave at this. Think of how these two are connected. at least at the intuitive level. Okay, thanks. In the class here. Yes. Hmm. So here also, like if A union B will be bigger, and you're adding smaller term to it rather than A and B together. Yeah, that's the lines, right? So A intersection B is bigger. So if it were cardinality, I didn't care. But here, because A union B is bigger, exactly, I've shown that in yellow. Adding the smaller one is not as effective if I had to measure the F on A and B individually. That's the intuition. Okay. Um, so maybe since you there's some other interesting properties. Maximum of submodular functions, are they submodular? Like maximum of convex functions, were they convex? Right? We saw that long back. Piecewise linear functions, right? Took their max. A minimum of concave functions. That's how we proved the Lagrange dual to be convex, right? Oh, sorry, concave always. Minimum of concave functions. Here, if you take max of convex submodular functions, is it convex? So think about it. This is a homework problem for you guys. Will the max of two submodular functions be submodular? Will the min of two submodular functions be submodular? Right? Are they like convex functions or concave functions? Same question. Okay. Think about this.